Hello, ladies and gentlemen. Welcome back to Physics 20, Chapter 8, Waves, Part 2. Now, I just finished the first recording, and I asked you to go to an applet, which actually was a GIF. I don't know. It's a horrible little animation where they showed you the dots moving up and down as the wave moves side to side. It sucked, but anyway, look at it. I hope you can see what's going on. And once again, if you were in class, it would be demonstrating this would make more sense. So if you're not in class, come see me when you can, and we'll play with the springs. This will make a little more sense. Anyway, now moving on, how are waves related to simple harmonic motion? Well, when a disturbance is made in a pond, a wave is produced. You drop that, now you drop a pebble in a pond, you get one ripple, one wave. I want you to realize the movement of the particles is up and down, but the direction of the propagation, that is the wave, is away from the source. Now if you look at the picture above, we have a little instrument that's making repeated waves, or technically transverse waves, because here you realize the particle is moving up and down as the wave moves away, to the right or to the left. Right? That's important. This is a transverse wave. Now, this movement can be represented with a line called a ray. So, you look at any point here, and you look out. You will see that the waves are moving away. Sorry, psychotic puppy. Now, there's some other things here. We can measure from crest to crest and get a wavelength, or from trough to trough, whatever's easier. There is a wave source in the middle. Each of these lines are crest, in betweens are troughs, and we have what we call velocity vectors. Now, we'll deal more with this later. I'm just showing you the picture and showing you hitting some of the stuff we want to talk about. Now, the important thing here is that rays are perpendicular to the crests of the... Try that again. My apologies. Rays are perpendicular to the crests of the wave. That is, the wave is going this way. What are you getting? Crests and troughs as the wave goes this way. This is a horrible drawing, trying to explain that to you. In class, we're all playing with springs and trying to not smack each other in the head. It makes more sense. But look at the diagram. Go along with me now. Now, in longitudinal waves, the particles move left to right when the waves move left and right. So particles. So here, now this is, oh God. I put a link in the Google Classroom. Click on this, and of course, there's a PDF. Now this becomes a excuse me, another one of those, I don't know, GIF particles. You can see the waves moving left to right and the particles moving left to right. I'm not going to try demonstrating this. I'm not going to try drawing it. Go look at it. You'll see what I'm talking about. But this goes back to here. These longitudinal waves, you get compression and refraction. Now, once again, we play with this in class, and you see the spots of compression and refraction where the particles are close together or far apart. Now, longitudinal waves are made up of areas of high particle density. That's a D, believe it or not. Compressions and low particle densities called refractions. So, right now in class, we're all playing with the springs, and you can clearly see this. That GIF or whatever, I don't know what the hell you call it. Demonstration I put online sucks, but it sort of gets the idea. Now, this is sound waves. Just realize you're getting spots where where particles are getting compressed, and spots where they're getting refracted, that is spread out. And notice from the middle of the compression to the middle of the next compression is the wavelength lambda. All right? Or you could measure it from the middle of the refraction to the middle of the next refraction, whatever. one complete cycle. And there you're getting, now, best example of this are sound waves. You've all stood in front of speakers and you can feel it vibrating in your chest. You're feeling the compressions, right? Now, some phenomena are made up of both transverse and longitudinal waves. Now, earthquakes are a good example of this. You will get what we call P waves, that is longitudinal waves, where stuff gets compressed, goes backwards and forwards. And then you'll get transverse waves where stuff goes up and down. Okay? Now, when you come back to school, you're watching this because I'm assuming you're not here at the moment. I want you to look at this. Look at Google Classroom. There are a couple of labs we're going to do. You get in groups, you play with those big springs, and you see these transverse and longitudinal waves. There's also an online lab that we're going to do tomorrow. So if you're not in class, you can do the online lab. All right? Any questions? Good luck. Otherwise, I'll see you in class soon.